Ever wondered how we can launch a 2.8 million kilogram rocket into space? It all boils down to the fascinating world of rocket science. This world, teeming with complexities and wonders, owes much to the pioneering work of Konstantin Tsiolkovsky in the early 20th century. His emphasis on efficient propulsion systems was a game-changer, laying the foundation for the rockets we marvel at today. From simple and reliable solid rockets to the more complex and controlled liquid-fueled ones, there's a whole universe to explore within these mechanical marvels. So ready to take a journey into the heart of a rocket? Buckle up! At the core of how rockets work is a simple principle: action and reaction. This principle, often associated with Sir Isaac Newton, is the driving force behind rocket propulsion. Picture this. A rocket sitting on the launch pad is like a tightly coiled spring, waiting to unleash its energy. When ignited, the rocket fuel rapidly burns, creating a forceful expulsion of hot gases. This expulsion, or action, propels the rocket in the opposite direction, or reaction. Think of it like a balloon. When you inflate a balloon and let it go without tying it, the air rushes out one end, causing the balloon to dart off in the opposite direction. That's the principle of action and reaction at work. In the case of rockets, this principle enables them to move upwards, defying Earth's gravity. It's a simple concept, yet it's the backbone of some of our most advanced technologies. But rockets aren't just about raw power. They are a marvel of precision and control. That's the basic principle, but there's more to it. Next, we dive into the engines. Rockets can have different types of engines. Some use solid fuel, others use liquid fuel. But what's the difference, you may ask? Well, let's dive into it. Solid fuel engines, as the name suggests, use solid propellants. They're quite simple and reliable, providing a consistent thrust. Imagine lighting a firework. Once it's ignited, it burns until it's completely out of fuel. That's essentially how solid fuel engines work. The simplicity of this design makes it highly reliable with fewer moving parts that could potentially fail. However, this comes with a trade-off. Once ignited, you can't really stop or control it. On the other hand, we have liquid fuel engines. They're a bit more complex, using liquid propellants that are mixed and ignited to produce thrust. The complexity of these engines allows for more control. You can adjust the thrust levels and even stop and restart the engine if necessary. This flexibility makes them ideal for missions requiring precise maneuvers. However, the increased complexity also means there are more things that could potentially go wrong. Now, you might be wondering why rapid ignition is so important. Well, think about it. You're sitting on top of a giant fuel tank. The last thing you want is for that fuel to ignite slowly or unevenly. A slow ignition could cause the rocket to veer off course, and an uneven ignition could lead to instability or even an explosion. Rapid, even ignition ensures that all the fuel burns at the same rate, providing steady, controlled thrust. So, solid or liquid fuel? It depends on the mission. Solid fuel engines are great for simple, straight-shot missions where reliability is key. Liquid fuel engines, however, provide the flexibility and control needed for more complex missions. Choosing the right engine can make a difference between a successful launch and a catastrophic failure. But how do we steer these rockets? That's a good question, and one we'll tackle in our next scene. Stay tuned. Steering a rocket is not as simple as steering your car. It requires precise adjustments and high-tech mechanisms. Now let's delve into how this intricate process works. When we talk about steering a rocket, we're really talking about adjusting its trajectory. This is the path the rocket takes as it travels from Earth into the outer realms of space. The goal is to maintain the most efficient route while avoiding any potential obstacles. This is where the magic of gimbaled engines comes into play. These are essentially rocket engines that can pivot, allowing for changes in the rocket's direction. Think of it like an extremely powerful and precise joystick. By tilting the engine in different directions, the rocket's course can be adjusted as needed. But it's not just about pointing the rocket in the right direction. Remember, we're dealing with an object that's moving at speeds that can exceed 25,000 miles per hour. This means that even the smallest adjustments can have a significant impact on the rocket's trajectory. This is why the process of steering a rocket involves continuous minute adjustments rather than one-time large-scale changes. In addition to gimbaled engines, rockets also use other mechanisms for steering. These include thrust vectoring, where the direction of the engine's exhaust is altered to change the rocket's path, and reaction control systems, which use small thrusters to create rotational motion. All these steering mechanisms work in harmony, guided by advanced computer systems and precise calculations. The aim is to ensure that the rocket stays on its intended course regardless of the external forces it may encounter. So, steering a rocket is a complex task that requires a deep understanding of physics and engineering. But now, you've got the basics. Rocket science may seem daunting, but we've just broken it down into digestible parts. We've navigated the complex world of rockets, from the basic principles that govern their flight to the intricate mechanisms that guide them through the cosmos. We began our journey by understanding the principle of action and reaction, the backbone of rocket propulsion. This principle, articulated by Konstantin Tsiolkovsky in the early 20th century, reminds us that for every action, there's an equal and opposite reaction. When rockets expel exhaust gases downward, they're propelled upward with equal force. Moving on, we delved into the heart of rockets, their engines. We compared the simplicity and reliability of solid fuel engines with the complexity and control of liquid fuel engines. Each type serves its purpose, with solid fuels offering steadfast thrust and liquid fuels providing greater control and adjustability. We then ventured into the realm of steering and navigation. We learned about gimbaled engines, the unsung heroes that ensure precise trajectory alignment. These mechanisms help rockets navigate through Earth's atmosphere and into the vast expanses of space. Rocket science might not be rocket science to you anymore. Remember, every journey into space starts with a single ignition here on Earth. Until next time, keep looking up.